So welcome to today's class. Today we will be talking about OFDM. For the next few classes, we'll be talking more details about the OFDM, how to generate it and other things, other details. So today we'll start with the first introduction to OFDM. I will also give a brief, tutorial on some FFTs and some basic DSP that's required for understanding OFDM. Okay, some basic properties of FFT we will do today. Okay, so let's go ahead and start. OFDM is one of the technology, one waveform in a class of waveforms called the multi-carrier systems. Okay. So you will understand why it's called a multi-carrier system in a little while. So OFDM stands for orthogonal frequency division multiplexer. Okay. So now most of you know that OFDM is the de facto standard for most cellular systems. For digital video broadcasting, it is OFDM. For, of course, Wi-Fi, it is OFDM. So, I mean, in some sense, OFDM has taken over most of the standardized cellular standards, at least. Okay, and there's a reason for that. It's actually very easy to use, and it provides good gains in terms of spectral efficiency also. Another important reason is it ties out very well with MIMO and forward error correction ports. Okay, the reason will become clear in a little while. Yesterday we saw why OFDM is required. Now, one thing was that when you have wideband channels and there is frequency selectivity, equalization becomes difficult. Okay, that's one of the major issues. One of the motivation factors for OFDM. And the second thing is, of course, you require multiple access schemes, and we have to see how OFDM will help in that. Okay? The basic idea of OFDM or any multi-carrier system is divide the spectrum. When I say spectrum, it's bandwidth. What is the bandwidth that's allocated into smaller bands. Okay. So when you divide the spectrum into smaller bands, what happens is each band looks like a flat channel. Okay. So what does it mean? Suppose you have a spectrum like this. Okay, this is your channel frequency response. Okay, so this is your channel frequency response, h of f in the frequency domain. Okay, of course this is frequency selective. Now you can see that there are dips somewhere, there are highs somewhere, and other things. But now suppose what you do is you divide this into small chunks, very, very small chunks. Okay, you go on dividing like this. Then if you now look at one of this chunk, okay, for example, if one of this bandwidth, one of these parts, what happens? This looks approximately flat. Yes, this looks approximately flat. And this approximation becomes better and better as the size of the bin decreases. Okay. So now what we effectively have is, depending on how many you divide, suppose you divide this into 1,000 small parts, we will have 1,000 flat channels. Okay, 1,000 flat channels. Agreed? And once they are flat, what is going to happen? Equalization of each flat channel is very straightforward. It's a single tap channel. You just divide by the channel coefficient. Yes. Okay. That's one issue. That's one issue. If you are able to divide like this, it's taken care of. Okay. And second thing is, we also saw in FDM, when you have some flat channels like this, this is what we saw. And when you have FDM, I mean, getting filters like this, very sharp filters, is impossible. So you have to do guard bands between each frequency band. Okay. We don't want to do that. I want my small flat channels in the frequency domain to be adjacent to each other without any guard bands. Okay, so no guard bands are required. No guard bands should be there. No guard bands between the parallel channels. Okay, So this is where OFDM comes into picture. Okay, so in OFDM, I mean, we will see how this is.
In this case, filtration will not be needed.
So essentially, you not require any filters. Okay, so you have, for example, you have 100 megahertz bandwidth. You divide into 1,000. What do you say? 1,000 bins. That each of them is 100 kilohertz now. So the 100 kilohertz are adjacent to each other. Okay, the 100 kilohertz will be adjacent to each other, and you will have 1,000 such parallel channels. Okay, this is the basic idea. The basic idea is in the frequency domain, you divide into small bins so that it effectively looks flat. Okay, so essentially you have multiple single tap channels. Okay, because of this, equalization is easy. Okay, and another important point which I'm not going to spend too much time is, these are parallel channels. There are 1,000 parallel channels. If you are able to allocate different modulations and different powers for these 1,000 parallel channels, okay, it becomes something called capacity optimal. What it means is, it means that you cannot do anything better than this. When you have a frequency selective channel, the best possible technique is to divide it into small frequency bins and allocate different powers and different modulation for each of this bin. Okay, this is also called as adaptive loading. Okay, by the way, generally adaptive loading is not used in wireless communication, but this is used in DSL modems. Extensively, it's used DSL modems. So DSL modems use OFDM with adaptive loading. Okay, adaptive loading means essentially each of the small bits, they use a different modulation, different QAM, and different power allocation. Okay, we'll see what happens in cellular systems later. Okay, just keep this in the back of your mind. I mean, this is not an important point. This is not very critical for our thing, but it's good to know that for frequency selective channel, this kind of OFDM is, in some sense, OFDM with power control and power and rate control is optimal. Okay, so with this introduction, what I'm going to do is I'm going to now do a little bit of recap of basic digital signal processing, specifically the FFTs. Okay, I just want to recap them because we're going to use them. Recap of basic DSP. In particular, I'll focus on FFTs. FFT or DFT, you can think of them, and I mean FFT is an implementation. Okay. So let X be defined as an n-length discrete sequence, discrete complex sequence. You can think of this as your discrete samples, complex samples. Sorry. Okay, this is an n-length sequence, starts at 0 and ends at n-1, so it's n-length sequence. Okay, be a n-length complex discrete sequence. Okay, then the FFT, n-length FFT of X is denoted by X tilde. I'm going to denote as a K. K generally I will use to I'll tell you. Let me first define this. Is 1 by square root n sigma n equal to 0 to n minus 1 okay. So essentially what we do, we take the sequence, multiply with this phasors, complex numbers, and add and sum it up. Okay, this is like almost like a Fourier transform, discrete version of your Fourier transform. Okay, this is called FFT. FFT is an implementation. People also call DFT. FFT is mostly an implementation thing, fast Fourier transform. But technically, you can think of this as a DFT also. And this is also, when I will say this is also DFT, discrete Fourier transform. Okay, FFT is just an implementation. Okay. Okay. So you can think of this as your discrete version of your Fourier transform. Okay. So your X of n, this is your time domain. When you do the FFT, what you get is the Fourier domain or the frequency domain. So I will denote that always by FFT. This is what I'm going to denote by. If I have a sequence n length sequence x, if I take an n length FFT, this is the what I mean by n length FFT. Okay. So your FFT converts from time domain to frequency domain. Okay. So what is now the inverse transform of this? The inverse transform of this is the IFFT. Again, I'm going to put for x tilde is defined as the output of IFFT will be time domain signal x of n 1 by square root n sigma k equal to 0 to n minus 1 x tilde k e power minus j e power j2 pi k n pi. Okay, so the only difference between this and this is a minus here. There's no minus here. Okay, j is nothing but square root minus 1. This is a complex j. I mean, instead of calling I am calling it j. Sometimes I use I, sometimes I use j. So just to recall, j is equal to square root of minus 1. Okay. Okay. So IFFT, what does it do? It takes a frequency domain samples. Frequency domain and converts it into time domain. Okay, is this definition clear? I'll give some interpretations of this, but is the definition clear? We don't have to use the definition anytime, okay, but just good to know this. That's there. Any questions?
No, sir.
Okay. So now let's understand what is the interpretation of this discrete Fourier transform. Okay, it is some, I mean, hand waving interpretation, what I call this. Okay, so essentially this is called, I'll call this a continuous time interpretation. Okay. Suppose you have a band limited signal. So suppose you have a band limited signal. Band limited signal g of t with bandwidth w. Okay, the bandwidth is w. Okay, and g of t, if you take the Fourier transform, you get g of f, capital G of f. Okay, so g of, you understand, all of you understand Fourier transforms. Okay, you have bandwidth w. Okay. Okay. So there was one question. Okay, that's a very actually good question. Mrs. Srivatsava is asking whether the denominator is 1 by square root n or n. Okay. Okay. So there is a reason why I defined that 1 by square root n. The reason is, if I put as 1 by square root n, what is going to happen is the energy in signal xn and the energy in the Fourier domain will be the same. Essentially, what I mean is, once I put this 1 by square root n, you can show that sigma mod x of n whole square, n is equal to 0 to n minus 1, is equal to sigma k equal to 0 to n minus 1 x tilde k whole square. Okay, so if I put 1 by square root n, the energy is conserved. This becomes a what do you say, unitary transformation. It's called unitary transformation. So in all my things, I'll put 1 by square root n, but MATLAB doesn't implement it like this. MATLAB puts 1 in FFT and 1 by n in IFFT. Okay, you have to take care of the scaling factor when you do assignments in MATLAB. Okay, but in the thing I teach in the class, I'll always put square root n so that the energy is conserved between the time domain and the frequency domain. Okay, hopefully that answers your question, Mr. Srivastava. Okay, so just coming back to this. So g of t Fourier transform is g of f. Okay, so essentially I'm just going to draw this. Okay, so this is my frequency domain and this is my Fourier transform. Okay, essentially I am going to say that this part is my bandwidth w. Okay, I am assuming that 0 outside. Okay, I mean, it's easy, difficult to draw, but I'm just assuming that. Okay. So suppose now I have a bandwidth w signal. What should be my sampling frequency? Given that this is bandwidth is w, what should be my sampling frequency to convert into discrete domain?
2W.
Huh?
2W.
Yes, sir. So essentially here we are not using half the bandwidth. So generally when we do 2W, it means half the bandwidth. But here the entire bandwidth is W. Okay. So the sampling frequency also will be W. Okay. So when you say 2W, it essentially what people do is they assume it's a real signal and they give this as W.
Yes.
Okay. Then you require 2W. But in general, we are dealing with complex signals. When you deal with complex signals, two-sided bandwidth, I call it as W. So the sampling frequency will be automatically be W. What you say is correct. 2W is a Nyquist theorem, but this is also same as Nyquist theorem. Okay. So the sampling frequency is W. So what this means is that I'm going to define my G of n. So my G of n will be equal to G of n by W. Every W 1 by, so sampling frequency implies sampling time is 1 by W. Okay. So G of n is defined as G of n by W. Okay. This is my time. And every n by W I sample it. Okay. N goes all the way. Okay. Now suppose I take a Fourier an FFT for this. An endpoint FFT, capital endpoint FFT. What that means? Okay. It turns out that this is equivalent except for a scaling factor to G of K times W by N. Okay. So I have my sequence G of N. I take N of these points and take an FFT, endpoint FFT. Then I get G of KW by N. Okay. So what that means is I define, so if you look at this, so if you just look at this particular thing, what it does is it's taking the bandwidth and dividing it into n parts. Okay. And I'm taking k is equal to 0, 2. So essentially remember what will you k be? K will be, k will be equal to 0, 1 up to n minus 1. That's what FFT does now. So, okay, so I did not write here. So k is equal to 0, 1 up to n minus 1. Similarly, n is equal to 0, 1 up to. Okay. So the output of an n-length sequence is an n-length sequence. Okay. Similarly, the output of an n-length sequence of IFFT is an n-length sequence. Okay. So what this means is, this means that you are dividing your bandwidth into n parts. Okay. And the width of each part, is, of course, W by N. And what you are having is these parts. This is the output of your IFFT. You are sampling the frequency domain at these points. Okay. So this is what is your this one. Is this clear? I mean, I want you to, instead of forget about the math, I just want you to get an interpretation of what happens when you take an FFT, you sample a signal and you take an FFT of it. How is it related to the Fourier transform of the signal? Any questions?
Okay. Here Fourier transform will be the sample or what?
So Fourier transform is a normal Fourier transform. So this is like defined as G of t e power minus j 2 pi ft dt.
Yes.
Okay, 1 by whatever, some square.
So that diagram what we have shown it, that we have sampled it, and then we are taking the Fourier transform. Then after that, what it will look like?
Okay, sir. So essentially, I have my G of t signal, which is a continuous time signal. Okay. If I take the Fourier transform, I get my G of f. This is one case. Now what I'm doing is I'm taking this G of n and sampling it. Okay, I'm sampling it at the 1 by W. In the time domain, I get my discrete samples. So once I get my discrete samples, if I take an FFT, I go into the Fourier domain, the discrete domain. This is what I get. This is exactly the Fourier transform. Okay, not Fourier transform, fast for FFT. What I'm saying is so this will be equal to my G of G tilde of capital K. This was my FFT output. Those are nothing but the Fourier transform, the continuous time Fourier transform sampled at some points. That's what I'm trying to say. So there's a relation between this, the FFT of the discrete samples and the continuous time domain Fourier transform. Essentially, you're taking the bandwidth and dividing by n parts. Okay, and taking the middle value of that. That's what I want to say.
This is discrete Fourier transform. Discrete is important here.
Yeah, this is discrete. This is FFT is discrete. Okay. Okay. So one more thing that you see is if I increase my n, I get better and better resolution in the frequency domain. Okay, just keep that in mind. It will come handy sometime.
Sir, is it power signal and energy signal like FFT, like Fourier transform? It's applicable for energy and power. So is this for both?
So there's no energy and power. Don't worry about energies and power. There is a signal x, g of t. What is my Fourier transform? This is my g of f. Okay.
Yeah.
You can sample g of t. Now you can sample g of t. Essentially, you are picking out values at n by w. At every n by w, you are picking 1 by w, 2 by w, 3 by w, 4 by w. You are picking them. Okay. When I get a bunch of those samples, I can take an FFT. Yes, you'll get some output. The thing what I'm trying to say is, what is the relation between this output of the FFT, discrete time FFT, versus the continuous time Fourier transform? Essentially, both. So G delta of k will be a sampled version of G of f, the frequency domain.
Okay. Okay.
Okay.
Yeah.
Actually, sir, she wants to say that whether energy will remain same or not. I think energy will remain same. Energy will be conserved.
Energy will be conserved, sir. Yeah, you're true. I mean, there's some scaling factors. I'm not putting those scaling factors. Except for a scaling factor, the energy will be conserved. You can show that.
Yeah.
Okay, but there's some scaling factors that we have to do. Okay, that time, I mean, I think that's not required at this point. That we really going to have to go into the depth about this. Okay. Okay. Okay, so this is one property that we have to remember. So there's a couple of more properties I have to tell you before we jump into OFT. Okay? One of the things is, so why FFT? Okay, why not DFT? FFT has very efficient FFT. When I say FFT, both IFFT and IFFT, that's what I mean. Implementation. Okay, so if I write the formula of FFT once, x tilde of k is equal to sigma n equal to 0 to n minus 1 x of n e power minus j2 pi kn by capital N. Okay, so and k goes from 0 1 up to n minus 1. Okay, so to obtain x tilde of 0, how many multiplications we should do?
Then we should not show the double summation, sir. That n is equal to 0 to n minus 1. For k also it is variable. So why don't you show that another summation part?
No, sir. No, sir. No, sir. So I am finding samples. So I am interested in x tilde 0, x tilde 1. This is my Fourier transform.
Okay. In that way, for every x tilde 0, you are varying k from 0 to n minus 1.
Yes, sir. N equal to 0 to n minus 1. Yeah.
Okay. Okay.
Okay. So to do each of this, so to just do the operation that is there here, it looks like you require n operations, n multiplications, n complex multiplications, and one summation. Okay. So to get all these n values, you require n into n square. Okay. So that is if you do it in a naive manner, n into n operations. There are some very, very efficient algorithms which can do this operation in n log n. Okay. Approximately that's linear in n. Okay. So the computers can do FFTs extremely fast. Okay. That's one of the reasons why FFTs are very, very popular. Okay, that's just remember this. The complexity, time complexity of computing in FFT is n log n and not n square. Okay, that's one thing. Okay, this is one property. This is property 1. Okay, so property 2 is very important. So I'm going to, so suppose I have a sequence x, which is an n-length sequence, and that is defined as x of 0, x of 1, x of n minus 1. Okay, I'm going to define a shift operator. Okay, it's called a circular shift operator. Circular shift operator. What does mean is, when I say shift a of x, what it means is you circularly shift the sequence by a places. Okay, so let's do an example. Okay, suppose your x is equal to just x0, x1, x2, and x3. Okay, so this is my x, 4 then. Okay. Then shift 1 of x would be equal to, I circularly shift. Essentially, what is going to happen? X of 3 is going to come here, and other things are going to remain the same. So essentially, it will be X of 3, X of 0, X of 1, X of 2. Okay.
Sir, you have shifting it by one place, na? So it should be x1, then x0, x2, x3.
So I'm going shifting the other way. So I'm shifting it this side. X3, sorry. Essentially, X3 is coming here. X3 is coming here. X0, X1, X2. It's shifting.
You are shifting from the back side.
Back side, yes. So suppose I do shift 2 of X. That will be X2, X3, X0, X0, X1. Okay, so on and so forth. Okay, I mean, so you understood the shift operator. Okay, so why the reason I'm taking the shift operator is,
Sir,
please, sir.
x2, then you are shifting for the two places. Then it should be x1, x2.
No, no. Essentially, two places got shifted now.
So it should be x1.
These two things came here.
Last two
came here.
Okay. You are taking the last two and then putting over there. Okay.
Yes.
In this way.
So shift 2x is nothing but shift 1x moved by one more point. So this one comes here.
Okay.
The reason why this is important is FFT of n length FFT of, you take a shift operator of a sequence, you take an a length a shift of a sequence x. This is equal to the FFT of the original sequence x tilde k multiplied by 2 pi ak by capital. Okay. So multiplying by a phasor, this is called a phasor, cos plus sine, is equal to shifting in the frequency domain. Okay, or if you're shifting the time domain, then the frequency in the frequency domain, what happens? It gets multiplied by a phasor. Okay, this is an absolutely very important property. Okay, just keep this in mind. Okay, so essentially, if I instead of doing FFT, if I do IFFT, everything will be the same, except that this minus will become plus. Okay, FFT and IFFT are very similar, except for a minus and a plus. Okay, this is one property. Okay? The other important property, which is important for equalization, is called circular convolution. Okay? So all of you know convolution. Huh? Convolution, what do you do? So you have when you have x of t, when you pass it through an LTI system h of t, you get an output y of t. Okay? And what is your y of t output? Y of t would be equal to convolution minus infinity to infinity x of tau h of t minus tau d tau. Okay? This is standard convolution. Okay, for any LTI, any filter or LTI system, we can think of this as an LTI system. Okay, this is the output input relation. In the frequency domain, what happens? If you take the Fourier transform of Fourier transform, what happens? You get y of f. What is the relation between y of f, x of f, and h of f? Y of f will be equal to x of f times h of f. Okay. So Fourier transform converts convolution to multiplication.
That is the beauty of Fourier transform.
Fourier transform, and this is exactly okay. So Fourier transform. So in the time domain, if you convolve, in the frequency domain it multiplies. In the frequency domain, if it convolves, in the time domain it multiplies. Okay. So essentially, what is said in technical terms is convolution plays very well with multiplication using Fourier transforms. Okay. So now I want to see if something similar holds true for FFTs and DFTs. Okay. Is it true that I can also define convolution for sequences now? I can say that y of n is equal to sigma x of m h of n minus 1 m equal to minus infinity to infinity. Okay, this is a discrete time convolution. Okay, is it true that FFT of y is equal to FFT of x into FFT of h?
No.
No. It's not true. It does not. So FFTs and convolution does not linear. This is called linear convolution, by the way. Okay, whatever we are doing is called linear convolution. Okay. So FFTs and linear convolution do not play well together. Unlike a Fourier transform and FFT, a Fourier transform and convolution in the continuous time domain. Okay. So what should we do? Okay, let's just understand this. I'm going to tell you a small example. Okay. So x of 0, x of 1, x of n minus 2, and x of n minus 1. Okay, I'm just putting all the things in line. Okay, so how do I do a convolution with my h? Essentially, what happens is I write my h of 0 here, h of 1 in the reverse order, maybe some h of m. Okay, let's think of this. The first thing, I mean, you assume that there are zeros all here, and you take the product of all these numbers and add them up. Okay, then you get your first output. That will be your y0. Then you shift this h by 1. Okay, you put next is h of 0 comes here, h of 1 comes here, and so on until h of m comes here. Okay, and then you go on shift. You essentially go on shifting the sequence to the right. Okay, and you multiply and add. That is what your convolution is, linear convolution. Okay, so what is circular convolution? Okay, you repeat this sequence. You repeat this sequence again here. You repeat this sequence again here. Essentially, you make it periodic. So what I do, I write my sequence again here. I write my x of n minus 1. I do x of n minus 2. So on this side. This side I say x of 0, x of 1, and so on and so forth. Then I do linear convolution. Then I put my sequence h0, h1, or hm, and I do linear convolution. Okay. When I repeat the sequence, when I repeat the one of the sequence periodically and then do linear convolution, I get circular convolution. Okay, that's called circular convolution. So essentially, you take the sequence, one of the sequences, you take the sequence, one of the sequences, you repeat it. Okay, and then do circular convolution, and then do linear convolution. Okay, that becomes a circular convolution. You can also write the formula for circular convolution. It's actually pretty straightforward. The only difference is essentially what you'll do is you will put mod capital N. Okay, modulus operator. Okay, anyway, let's not worry about this right now. So you understood how a circular convolution happens. Circular convolution is the same as linear convolution, except that you repeat one of the sequence in the front and the back. Okay. So I am going to denote the circular convolution of two sequences as x circularly convoluted with h. X of n circularly convoluted with h of n. This is equal to my y of n. Okay. So why is the circular convolution important? It turns out, okay, I will say that what is circular convolution is defined as m equal to n length circular convolution, x of m, h of n minus m n. Okay, when I say n minus m n, it implies this is equal to mod of n minus m comma n. Mod means essentially when you divide n minus m with n, what is the remainder? There is nothing but the remainder. Okay, so mod of 5 comma 3 will be, when you divide 5 by 3, what is the remainder? You get 2. Okay, mod of 5 comma 4 will be 1. Okay, mod of 5 comma 5 will be 0. Okay, so modular, it's called mod operator. Mod operator is nothing but remainder. Okay, and you denote this is the circular convolution is denoted as x circularly convoluted with h. Okay, why am I telling you this? FFT of endpoint FFT of y will be equal to endpoint FFT of x into endpoint FFT of h when you circularly convolve. Okay, so essentially circular convolution of discrete sequences plays well with product is equal to product of, I mean, in the Fourier domain is equal to product of FFTs. Okay. So like how FFTs got, I mean, Fourier transforms got multiplied in the frequency domain for continuous time signals for a convolution. Circular convolution is, for circular convolution, FFTs of those sequences get multiplied. Okay, is this clear? So, I mean, what I wanted to take from this whole thing is, I mean, forget about the formulas and other things. Essentially, what is circular convolution? Circular convolution is nothing but you repeat one of the sequence to the left and the right, and then you do linear convolution. That is called circular convolution. And when you do circular convolution, FFTs of the output is nothing but the product of FFTs of both the sequences. Okay. Any question? Why this is important will become clear. Okay, so this is one of the very important things. I mean, we do something for this.
Is this used in the cyclic prefix? The same philosophy?
Yes, that's the concept. That's why you repeat it. Okay, I'll come to this. I'll come to that in great detail.
Okay, right.
Okay. Okay. Any other comment, question, please? Okay. Okay. So with this background, we can start OFDM. You have bits. So I'm going to draw the transmit and the receiver chain for OFDM. Okay, then we are going to discuss property by property. We will discuss all the properties. Sorry. Okay, you take bits. First, you map it to some constellation point. Okay, some constellation. Okay. So, for example, the constellation can be PPSK, QPSK, 16 QAM, whatever fancies us, whatever is important. Okay. You can also have multiple constellations. Also, we'll come to that later. Then at this point, what do you have? You have complex numbers, no? IQ samples. What you call IQ samples are complex numbers. Okay. Just hold on 1 minute, please. Then you do something called serial to parallel converter. S by P means serial to parallel converter. What it does is very simple. So essentially, these are going to come in the other way around. No? First, x of 0 is going to come. Then x of the last n minus 1, and so on. So there are more things like this is going to come. Okay. What it's going to take is it's going to take every n of this and put them parallelly. That's all. Nothing is going to do. It's going to do x of 0, x of 1, x of n minus 1. Okay. So now you have an n-length sequence. What you do is then that's fed into an IFFT. Okay, we saw IFFT. Just before we saw what is IFFT, no? Okay, we saw what is IFFT. IFFT and FFT have the same properties. Remember that, all this. Similar properties, not same. Okay. So it's fed into IFFT. Okay. So after IFFT, you get again n outputs. You take an n-length IFFT. Okay, I'm going to put n. Okay, n-length IFFT. Okay, so you get n outputs. Okay, call that as y of 0.
Excuse me, sir.
Yes, please.
Sir, why it is fed to IFFT? Because it is already in time domain, na, sir?
Yeah, no. I'll come. That's a very good question. I'll just give you 1 minute. I'll explain you that. Okay.
Okay.
Y of n minus 1. Okay. So IFFT, when you do this in IFFT, you take n points and you get output n points. Then what you do is you have something called parallel to serial converter. Okay. What does parallel to serial converter do? It takes, it's opposite of serial to parallel converter. Okay. So essentially you get output as y of 0, y of n minus 1. Okay. And then you have a block called CP addition, cyclic prefix addition. Okay, I will tell you what cyclic prefix addition is in a little while. And after that, you put it to your RF. Okay, RF. I'm just going to write RF, and of course, this is going to go to the antenna. Okay, these are your IQ samples now. Okay. So first let's understand the blocks. I'll also draw the receiver chain and then we will discuss. Okay, this is the transmit chain. Okay. So on the receive chain, what happens? I'm going to start on the other side. Maybe I'll start here. So you get your antenna, and then there's some RF, LNAs, PA, LNAs, and other things. You get your IQ samples. Then first thing you do is again you do serial to parallel converter. It's going to give an output 0. I'm going to say. Okay. Then you pass that to FFT, an endpoint FFT. Okay. And then you get again n samples. You do parallel to serial converter. Once you do parallel to serial converter, then you do a demodulator, the standard demodulator that we were looking at earlier. Okay, you get some points because of noise and other things. You do a demodulator. And the output of demodulator will be bits or LLR values. Okay, the FPC and other things, we'll come to that later. Okay, let's just focus on okay, you get bits. Is this clear? Okay. So in OFDM, just to answer Mr. Chitranjan's question, this is the frequency domain. See, you always transmit time domain. You always transmit time domain signals, huh? You always transmit time domain signals. Yes? This is all time domain, because in RF, finally you have to transmit time domain signals. So when you put an IFFT, so this should be frequency domain. Okay, so this will be frequency domain. Okay, so in OFDM modulation, you are mapping your information in the frequency domain using an IFFT to convert into the time domain and transmitting the time domain IQ samples. Yes?
Certainly.
Yeah, on the receiver is opposite. You get your time domain signals and you do an IFFT and you do an FFT to convert it into, this is the time domain.
Frequency domain.
And you convert it into frequency domain. And you demodulate in the frequency. You demodulate the information in the frequency domain. Okay? So this is a little bit different from what we have learned before, where their information was modulated in the time domain. Rather than that, you modulate time. You modulate information in the frequency domain. The information is there in your bits and the constellation points. Huh?
Excuse me, sir. Sir, that you mentioned at the transmitter that is in frequency domain, but
yes.
Before that the constellation mapping is done. But
No.
That is in time domain, na?
No. The constellation. So this is interpretation. FFT, IFFTs are operation. So anything before IFFT is in the frequency domain, after IFFT is in the time domain. Okay. So this whole thing is in the frequency domain. Okay. Essentially, your information you're mapping to some points.
So even constellation itself is the frequency domain.
Is in the frequency, and the constellation points are mapped to the subcarriers in the frequency domain. Okay. And then you take an IFFT to convert into time domain signal, because you can only transmit time domain signals in actual real life. Okay. So you transmit the time domain signals, you receive the time domain signals, you again use an IFFT to convert into the frequency domain, extract out the information and transmit it. Okay.
So where are the subcarriers here?
I haven't thought about. I will tell you. Okay, these will become your subcarriers. I'll tell you all that. Okay, I'll tell you all that. Okay. Okay. So I'm going to stop now because. Okay, I'm going to stop now because the next thing is cyclic prefix addition and bandwidth of the signal and other things. Before I move, I'll do it in the next class. Okay. So today I'm going to. Sir, Pandey sir, please.
CP addition that we have put in that part.
Okay, CP addition. I actually forgot one block here. Just 1 minute. Sorry. Here there's an CP removal also.
Yes, there should be. But what is CP addition or removal?
So CP addition, CP removal. Sir, I will give a detailed description of this in the next class. So in short, what it does is it takes something from the back and adds into the front, so that linear convolution becomes circular convolution for the channel. Okay, I will explain that in the next class in detail. Okay, we'll go through that. Okay, so that is what it's called cyclic prefix addition. It's essentially nothing but you take the last few symbols and add it to the front so that the channel acts like a circular convolution. Okay, but we'll come to that in a little while. Okay, so what I want you to
sir, one small.
yes, sir, please.
Sir, if it is just a representation in frequency domain, then why we are again here talking about time domain?
So essentially, you should remember we can only transmit time domain signals. Yes. So the interpretation is anything before FFT is frequency and after FFT is time. Okay. So it becomes what is going to happen is if you look at this picture, this picture, I said that you are going to divide your frequency into bandwidth into small parts. Yes. And this acts as a single carrier channel, whatever, single tap channel. What I'm going to do is instead of doing this in the time domain, I'm going to actually modulate the data in the frequency domain using IFFT. Okay. So I'm going to do this in the next class in detail. Okay. I just introduced you what IFFT is. You please have a look at this once more. Okay. I think you should think about all the blocks once more. In the next class, I'm going to tell you what is the bandwidth of the signal, what is meant by cyclic prefix, how is the interpretation of modulating the subcarriers in the frequency domain. We're going to do that in the next class. Okay.
Sure, sir.
So,
you can answer, sir. If it's possible, next class kindly explain us, sir. Because if it is just a representation, so here also time domain signal exists. So again, we are
Alex, it's a represent. Everything is a representation, but it's an interpret. It's the way. I mean, it's like a notation. We interpret this as a frequency domain. Okay, there's nothing called a frequency domain by definition. Nah? We just interpret this as a frequency domain because it comes before IFFT. Okay, and there's a logical reason for that also. I mean, it will become clear in the next class. Okay, once I explain you the spectrum and other things.
Okay, okay, thank you, sir.
Okay. So I'm going to give one assignment today. I mean, just it's a small set of 3-4 problems. These are not MATLAB based. These are things to understand what is sampling, what is bandwidth, how do you compute SNR and other things. I'll give you 1 week's time to finish that. Okay, today by evening I'll post it. From there you'll have 1 week's time to finish that. Okay, all of you. Okay, that will be a graded assignment.
Yes, that is good, sir.
Okay, it will just small problems, 5-6 problems, and MATLAB assignment is also going to be uploaded. That you can take time, and that we will see how to grade and other things later once the MATLAB is installed. Okay, I encourage everyone to do the MATLAB also. Okay, but that's something different from this. Okay, so thanks everyone. I'm going to stop now. I'll see you in the next class.
Thank you.
Thank you, sir.
Bye everyone. Thank you.
Thank you, sir.
Thank you, sir.